Hello everyone. What we'd like to do in this video here, or what we're going to be doing in section 2.7, is we're going to be learning how to combine functions. We want to take two functions, we want to know how do we add functions, how do we subtract functions, how do we multiply functions, how do we divide functions, and how do we compose functions. Now, whenever we're doing those type of exercises, the one thing that we're always going to be asking ourselves is what is the domain of the resulting function? So before we get into that, let's go ahead and take the time in this video to review how to find the domain of a function. Now, the domain of the function, or domain of a function, is all the values of x that I'm allowed to plug into the function that give me out a meaningful output. By meaningful means it's actually going to plug out, it actually is going to give me an output, or in this case it's going to give me a real output. Let me give you a couple examples. So, for example, if we think about the function f of x, which is equal to about 3 over x minus 2, notice for this function that the value 2, if I try to plug it in, sorry, there's a 3 up here, I'll get 3 over 0. Now, this should be making your math brain go crazy. Remember, we cannot divide by 0. So when I plug in 2, for example, 3 divided by 0 is undefined. There is no output when I plug in 2. Now this should make sense because if you were to graph this function, like we kind of graph these type of functions in section 3.6, there is a vertical asymptote on this function at x equals 2. There's no output there, so 2 is not in the domain of this function. Something else we need to watch out for is, let's say I have another function, let's call it g of x. And let's say, for example, it's something like the square root of, I don't know, how about x minus, 7 or something like that. Notice that if I try to plug in, how about 3, for example, this would be the square root of 3 minus 7, or we're going to get the square root of 3 minus 7, what is that, negative 4? Notice here that we can't take the square root of negative 4. Now, if we kind of pause here to say, really for the rest of this class, we're only going to be caring about real numbers. So in this case here, when I plug in the value of 3, the function is not outputting me a real number, it's outputting me an imaginary number. So for the purposes of the rest of the class, it's not giving me a real output. So here we'll say, this is no real output. So in that case here, we would say that 3 is not in the domain of this function because it's not outputting me a real number. So what we want to be able to tell the reader when we're reporting the domain of a function is we want to report to the reader all the values of x that you're allowed to plug into the function. And we also want to make sure that when we report this to our reader, that we report it in the simplest possible way. So let's do a couple examples about how to do this. So I hope to give you really two things we have to watch out for when finding the domain of the function. I like to think that there are these rules for math, or there are these math gods, and then they told us that there are these math commandments, like thou shalt not do these things. So these are called the domain restrictions, or the golden rules of math, or the commandments of math. The domain restrictions. A list of things that we have to watch out for. Okay, the first thing that we have to be careful of. Now this is just going to be a list so far. Someone write it. So far. Okay, so the first thing is that we can't divide by 0. The math gods say, thou shalt not divide by 0. So one thing is we can't divide by 0. Okay, that's one thing we got to watch out for. The second thing we can't do is we can't take the square roots of negative numbers. We're not, imaginary numbers and complex numbers aren't invited to the party for the rest of the class, until the final. So what we do is we can't take the square roots of negative numbers, but to be more general, we can't take the even roots of negative numbers. For example, let's say, notice that we can't take the square root of negative 4 because there isn't a real number that I can multiply by itself twice to get out negative 4. 2 and 2 don't work, that gives me 4, and also negative 2 and negative 2 don't work, that also gives me 4. There's no real number that I can multiply by itself to get out a negative. Similarly, I can't take this, like the fourth root. I can't take the fourth root of negative 16 for a similar reason. Well, this can't be 2, because 2 times 2 times 2 times 2. What is that? 2 times 2 is 4, times another 2 is 8, times another 2 is 16. Okay, that didn't give me negative 16. And the same thing as if I put negatives here. Negative 2 and negative 2 is a positive 4, times another negative 2 is a negative 8, times another negative 2 is a positive 16. So this is not a real number. I cannot take an even root of a negative. Now it's totally fine for me to take the odd root of a negative. For example, the cubed root of negative 8 makes sense because the answer should be negative 2. Because negative 2, what number times itself 3 times gives me out a negative 8? Well, negative 2. Negative 2 times negative 2 is positive 4. Positive 4 times a negative 2 is a negative 8. So I can take odd roots of negatives, but I can't take even roots of negatives. And that is the second commandment of math. We can't take the even root of a negative number. Okay, let's do a series of examples to get us comfortable with doing this. Okay. We'll start simple, and we'll spice it up. Okay. Let's say, for example, so for all these examples, we're going to find the domain of the following function. Okay, so for the first example, let's say we have something like f of x is equal to, how about the square root of, let's do 3 minus 2x. Okay, so if I want to find the domain of this function, I need to go through our list. Well, in this example, I'm never going to be worried about dividing by 0 because this function doesn't have a denominator, and specifically it doesn't have a variable in a denominator. So I'm never going to divide by 0. However, I am worried about taking the square root of a negative. Now, what needs to be true here for that not to happen is whatever is inside of the square root or the argument of the square root has to be positive. So what I need to make sure of is I need to make sure that 3 minus 2x is bigger than or equal to 0. Bigger than or equal to 0 because the inside can be 0. Notice that the square root of 0 does make sense. The square root of 0 is 0 because what number times itself twice gives you a 0? 0 times 0 is 0. So this is what I need to have, this is what I need to be true. 3 minus 2x has to be positive. So when I'm solving an inequality, at least in this case, for something that's linear, we can solve it just like an equation, but we have to remember when we solve inequalities, it's just like solving equalities or solving equations. We just have to remember if I ever multiply by a negative or divide by a negative, I gotta flip the sign on the inequality. So let's go ahead and solve this so we could subtract 3 from both sides. So I'll get out that negative 2x is greater than or equal to negative 3. You could divide both sides by negative 2. We need to be careful, we divided by a negative, so here x has to be less than or equal to 3/2. And this is the domain. So notice that if you just want to test this, I don't know, this is saying that x needs to be less than or equal to 1.5. So plug in a number bigger than 1.5. Let's say we plug in 2. Well, notice 2 won't work. 2 is not in the domain of this function because if I plug in 3 minus 2 times 2, that's 3 minus 4, that's negative 1. I can't take the square root of negative 1. Okay, we could test it by, plug in a number less than 1.5. Plug in 0. Well, if I do 3 minus 2 times 0, 3 minus 0, I get out 3. I can take the square root of 3. So our domain, I can plug in anything less than or equal to 3/2. Now, while this is a simple example, it's always going to be good for us to sketch the domain on a number line. So if I'm sketching the domain on a number line, you don't have to mark 0 on your number line, but let's mark 3/2. So here's 3/2. I guess if you want, you could put 0 here. You don't have to. But I need all x values that are less than or equal to 3/2. This arrow is saying I want all x values that are to the left of 3/2. So I'll put an open or a closed dot over 3/2, telling the reader I can include 3/2 in anything less than 3/2. So this is the domain. Okay, we can write this in 3 different ways, the domain. We can write it in what's called set builder notation. This is set builder notation is the most common notation you'll see if you go further on in math. And it's actually my preferred notation when doing domains. So the way set builder notation works is we'll first start with a curly bracket. We'll say x, so I need all x such that, well, then I'm just going to write the condition, x has to be less than or equal to 3/2, and then I'll close the bracket. This is called set builder notation. So I'll write that. This is called set builder notation. There's also interval notation, or let's do inequality. There's inequality notation. Inequality notation is just like set builder notation, you just don't have the brackets. So you could just write x could be less than or equal to 3/2. An equivalent way to write this is you could also say that x is what? It goes from negative infinity, all the way up to x, and then x all the way up to 3/2. So I'm including 3/2, but notice I'm not including negative infinity. It's a strictly less than, because, well, negative infinity isn't a number. It's just saying, hey, you're going this way like forever. So negative infinity is nothing you'll ever reach, so you're not going to be including negative infinity. So from negative infinity all the way up to 3/2, including 3/2. Or there's interval notation. Interval notation, and here we just use brackets. So what I would do here is I would put a soft bracket on negative infinity. So soft bracket goes with strict inequalities, and a square bracket goes with less than or equal or greater than or equal to the inequality signs. So I would write a negative infinity with a soft rounded bracket, and I put a comma all the way up to 3/2, and I put a hard bracket. So from negative infinity, not including negative infinity, all the way up to 3/2, including 3/2. So this is the three type of domain notations you may see. Okay, let's do another example. Let's spice it up a little bit. Okay, let's say for our next example, let's say we have the function, how about f of x, which is equal to, how about the square root of x minus 3 all over, how about x squared minus 2x minus 8. Go ahead and pause the video and give this one a shot on your own. Okay, so there are two things I'm worried about here. I have variables in a denominator, so I'm possibly can find a value of x that'll make me divide by 0. I also need to make sure that I plug in values which make what's inside the square root positive. So there's two things I have to take care of. So what I'm going to do here to figure out where the denominator is 0 is I'm going to factor the denominator. So here we have the square root of x minus 3. Okay, what will we have in parentheses here? We'll have an x. Okay, I think I need a 4 and a 2. So they got a multiple. One of them has to be negative. The bigger of them has to be negative. So the first thing we need to pay attention to is notice that x can't be equal to 4 and x cannot be equal to negative 2. If I plug in 4, I'd be dividing by 0. If I plug in negative 2, I'd be dividing by 0. These are not in the domain of the function f. This should make sense because those were the vertical asymptotes of this function would be. Okay. The other thing I should be careful about is I don't want to divide by, or I don't want to take the square root of a negative number. So whatever is inside of the square root, specifically x minus 3 has to be bigger than or equal to 0. We could add 3 to both sides, and we get that x has to be greater than or equal to 3. So we have 1, 2, 3 conditions we need to look at. Now what I don't want you to do is just write these down and not think about it. Because if you were just to say, I guess in set builder notation, oh, it's just all x such that, well, x can't be 4, x can't be negative 2, x also has to be greater than or equal to 3. Okay, I hate this. I hate this. You're not being kind to the reader. Notice, you're saying, hey, x has to be bigger than or equal to 3. So why are you telling me that x can't be negative 2? Saying that x has to be bigger than or equal to 3 is already telling you that x can't be negative 2. Be nice to the reader. Don't include more information than you need. That's why I highly recommend sketching these. So if I were to sketch these, it'd be a little bit more clear. I do this every time. I need x to be bigger than 3, so let's mark 3 here. Okay, I can include 3, anything to the right of 3. Okay, x can't be 4. X can't be 4, so I'll put an open dot here. And x can't be negative 2. So hopefully we can see here that I don't need to include negative 2 because I'm already telling the reader I need to be at values bigger than 3, and all I need to tell the reader is x needs to be bigger than 3 and exclude 4. So if we're going to write these in the 3 different types of notations, let's go ahead and do that. So one way I can do that in set builder notation, which I already have written, we'll just write it again. It'd be all x such that, how about x is bigger than or equal to 3, and x cannot be equal to 4. Okay, if we wanted to do this in, let's say, in equality notation, I would have to break it up into 2 pieces. I'd have to tell the reader that, let's see, x can be between 3 and 4. X can be between 3 and 4. I can include 3, but I can't include 4. I guess just notice how this reads. I'm saying that x lives in between here, and those arrows should kind of guide you. Notice that 3 is to the left of 3 is to the left of x, and x is to the left of 4. So x, how this reads is x is between 3 and 4, including 3, not including 4. Okay, so I have to do this region, but I also have to include this region over here. So oftentimes we just write the word or x could be bigger than 4. You could write x could be bigger than 4. Equivalently, you could say that x is between 4 and positive infinity. Okay, we could also write it in what's called interval notation. So the way we would do that is I need to include from 3 to 4. We're including 3, so I'll put a hard bracket and a 4. We'll put a soft bracket. And instead of putting the or, we use this U symbol. This symbol is the mathematical symbol. It means the word union. But for our purposes, I'll talk more about this in a second, I guess in the next video. But you can just read this as a mathematical symbol for the word or. So I can be between negative 3 and 4, including 3, not including 4. Or I could be between 4 and infinity. So either one of these notations here would work. Okay, here's our next example. Go ahead and pause the video and give this one a shot on your own. Okay, so I have 2 different square roots here I need to pay attention to. Okay, notice here I'm never going to be worried about dividing by 0 because I don't have a denominator. I also don't have a variable in the denominator, so I'm not worried about dividing by 0. Okay, what I need to look out for though is we're looking right here, I need 3 minus x to be bigger than or equal to 0. Okay, if you solve this, you should get that x needs to be less than or equal to 3. Similarly over here, what I need x plus 2 to be bigger than or equal to 0. If you subtract 2 from both sides, we need that x needs to be bigger than or equal to negative 2. So what we're going to want to do here is we're going to want to draw a number line. So I don't want you to tell the reader x has to be less than or equal to 3 and x has to be bigger than negative 2. We want to write that in a nice way. So I need x to be less than or equal to negative 3. So here's positive 3. I need x to be less than or equal to positive 3. Sorry, this is a 3 here. So less than or equal to 3. And I also need x to be strictly bigger than negative 2. So here's negative 2. Okay. So for this example here, I need to find the region that works for both of these functions. And the region that's going to work for both of these pieces here is the overlap. So what we want to tell the reader is we can plug in values between negative 2 and 3. So the way we'll write this is we'll write this as a compound inequality. So if we want to use set builder notation, let's erase a little bit of this here. Okay. So I'm writing x because x lives between negative 2 and 3. Well, in set builder notation, we would say all x such that, well, negative 2 is to the left of x. Negative 2 is to the left of x. So x can be, x And negative 2 is always less than x, but x can possibly be negative 2. And x is also to the left of 3. So here x can be between negative 2 and 3. It can be negative 2 and it can be 3. Okay, so this would be set builder notation. We could also write, let's say, we could also say, let's say an inequality notation. We would just write x needs to be between negative 2 and 3. And if we wanted to use interval notation, we would write negative 2 to 3. Okay, let's do another example. We want to be paying attention. We always want to be drawing the number lines. Okay, let's just alter this one slightly and show you how not writing a number line can get you in trouble. So let's say we have something like, let's put 3 minus x and then x minus 5 here. Go ahead and give this one here a shot. Okay, so what needs to be true here is we need 3 minus x to be bigger than or equal to 0. So we must have x has to be less than or equal to 3. And we also need x minus 5 to be bigger than or equal to 0. Or add 5 to both sides. We need x to also be bigger than or equal to 5. So if I'm sketching this on a number line, okay, here we are at 3. So here's 3, and here is 5. Okay, well, x can be less than or equal to 3, or x can be bigger than or equal to 5. Okay, so I need to find what values of x work for both of these pieces. So I need to look for the overlap, but there is no overlap. There is no value of x here that'll work for both of these functions. This function is broken. This function is broken. This is a broken function. This is a broken function. This is a problem. So notice that this would be so mean for you to just not think about what's happening and for you to write, I don't know, what if you said, let's erase some of this. Let's erase some of this. If you were to say, oh, the domain is all x such that x is less than or equal to 3 and x is greater than or equal to 5. If you reported this to the reader, man, the reader's going to be really pissed. Why would you tell the reader, hey, x less than or equal to 3 and x bigger than or equal to 5? You're like tricking the reader to think that there's something in this set, but there is nothing in this set. The reader's going to be pissed. He's like, why did you just tell me that this function is broken? Don't be mean to the reader. Don't be mean to the reader. So you could write the domain in a few different ways for this type of function. You could say all x such that, you could just say no real numbers. You could just say no real numbers. Or another way to write this is just to put a circle and a line through it. This symbol here means empty set. So the domain of this function is the empty set. There's nothing in it. Okay, let's take a look at this next example. In this one, I'd like to compare the differences between finding the domain of f versus finding the domain of g. Notice that these functions are pretty similar. Notice for this one, I have the square root distributed in the numerator, and I have the square root distributed to the numerator and denominator. Here, I have the 3 minus x over the square root of 4 minus x all inside of the square root. Okay, so let's do these each separately. If you'd like, pause the video and try this out on your own. Okay. For this first example, there's two things I'm worried about. I'm worried about 3 minus x being negative. So I need to make sure that 3 minus x is bigger than or equal to 0. If we solve this, we need x to be less than or equal to 3. At the same time, I need 4 minus x. I need 4 minus x to also be bigger than or equal to 0. But be careful, I don't want it to be bigger than or equal to 0. I want it to be strictly bigger than 0. If 4 minus x was 0, I'd be taking the square root of 0, which is 0. I'd be dividing by 0, which is a problem. So if we go ahead and solve this, you would get that x needs to be less than 4. So we'll want to take a look at a number line here. Okay, so I need x to be less than or equal to 3. And I need x to be strictly less than 4, so I'll put an open dot over 4. So I need to find the region that works for both of these functions, both of these pieces, and that's going to be in the overlap. So I need to find values of x that satisfy this equation, this inequality, and at the same time satisfy this inequality. So if x is less than 3, it's less than 3, and it's less than 4. Notice I can't plug any number between 3 and 4. Like if I plugged in 3.4, well, I can plug 3.4 into this piece, but I have a problem plugging into this piece. So I need to look for the overlap. Okay, so if I were to write this in our domain notation, okay, let's go ahead and do that. What I would want to tell the reader is all x such that, well, x could be less than or equal to 3, and that's it. Or I could tell the reader that x could be between negative infinity and 3, not including negative infinity, including 3. Or it can be from soft bracket, from negative infinity all the way up to 3, hard bracket on 3. You could also equivalently just say right here, just as a note, you could equivalently say that just x needs to be less than or equal to 3 if you'd like. So that's our first example here. Let's take a look at the other one. Now, what we need to be careful about this other example is you need to be careful about distributing square roots. In general, the square root of a over b is equal to the square root of a over the square root of b. You can do this provided that both a and b are positive, or provided that both a and b are positive. So we just need to be a little bit careful. And the reason here is because when I have these separated, well, I could have a problem with this piece, and I could have a problem with this piece being negative, I could have a problem with this piece being negative, but if they're under the square root and both of them are negative, that creates a positive which could work. So these will actually be different. Okay, so what we're going to want to do for this one here is what I need to look for is I want to know when is 3 minus x over 4 minus x, when is this bigger than or equal to 0? So this is a rational function. I want to know when this rational function, if we were to graph it, is above the x-axis. So what I want to do here is I'm actually going to want to make a sign chart. This function here, it can only flip from being positive or negative by either crossing through the x-axis. So I'll want to look for when this function is 0. And I'll also want to think about, it could also possibly, flip over the axis with an asymptote. So it could be positive on one side of the asymptote and flip to negative on the other side of the asymptote. So we're going to make a number line here, and I'm going to look for the x-intercepts and the vertical asymptotes. So this will be 0. I'm going to get an x-intercept when x is equal to 3 when the numerator is 0. So I could put a 3 here. Okay, and I'm going to record a z over the top to remind me that that's where a 0 is. That's when the function is 0. Also, when x is equal to 4 here, if x is equal to 4, the function is undefined there. So you could put a u here if you like for saying that the function is undefined there. It should also be telling you that there's a vertical asymptote here. So z for a 0, u for undefined. Now the graph is only going to be able to flip sign by crossing over 3 or crossing over 4. So let's think about what's going on here. And what we can do is we can make a sign chart for each of these regions. So let's first start by picking a value less than 3. So if I pick a value less than 3, how about x equals, I don't know, it could be, how about 0, for example? Well, if I plug in 0, I'm going to get 3 minus 0. I'm going to get a positive answer. And I'll get a 4 minus 0. I'll get another positive answer here. So I'm going to get a positive over a positive. So the graph should be positive in this region. Okay, if I'm between 3 and 4, I guess one way you could think about it is the multiplicity of the 0, 3 is 1, so it has to cross through. If you don't like that argument, you could pick a number between 3 and 4. How about like 3.5? So 3 minus 3.5 is a negative number, and 4 minus 3.5 is a positive number. A negative divided by a positive is a negative. And now we can pick something bigger than 4. So how about x equals 5, for example, something bigger than 4. I mean, if you're thinking about this asymptote here, this asymptote has a multiplicity of 1, so it has to have opposite action, so it should be positive over here. Or you could check a number bigger than 5. 3 minus 5 is a negative number. 4 minus 5 is another negative number. A negative divided by a negative is a positive. So we actually have something different for this example. We actually have that I can plug in numbers into this function for numbers less than 3 or bigger than 4. I need to be a little bit careful with my signs though. Here, I need x to be less than or equal to 3 because when I plug in 3, this piece is just 0. And I need x to be strictly bigger than 4 because if I'm right at 4, I'll be dividing by 0. So if we're writing this, I can't write it as a compound inequality, so I'd have to write this as all x such that, well, x could be less than or equal to 3, comma, x could be greater than 4. You could also say that x needs to be between negative infinity and 3, or x needs to be between 4 and positive infinity, not including 4. If we want to write this in interval notation, we would put a soft bracket, so negative infinity up to 3. We put the union bar, and then we write soft bracket on the 4 all the way to positive infinity. So that's how we'd write the domain of this example here. So be careful with square roots. Okay, let's say we have some sort of crazy polynomial under our square root. So let's say, for example, that we have f of x is equal to the square root. Let's say we have something like x cubed, how about minus 5x squared plus 6x. Let's say I want to find the domain of this function here. So I'm not worried about dividing by 0, but what I am worried about is taking the square root of a negative. So what I need to be true here is I need x cubed minus 5x squared plus 6x. I need this to be bigger than or equal to 0. So we have a polynomial here, and I want to know when this polynomial is above the x-axis. We could sketch this, or we could make a sign chart. So what I'm going to do is I'm going to go ahead and factor this. So it looks like I can pull out an x, and I'd be left with x squared minus 5x plus 6 would have to be greater than or equal to 0. Or to have x, I'll put some parentheses here, so x, let's see, what would work here? I need combinations. Let's see, I think I need a negative 2 and a negative 3. They multiply to give me positive 6, they add to give me a negative 5. So I want to know when this is greater than or equal to 0, so we'll make a sign chart. Okay, well, when is it exactly equal to 0? Well, that's when x is 0. How about when x is 2 or when x is 3? These will all be locations where the output of the function is 0. So now I just need to test points within these, looks like 1, 2, 3, 4 regions, or we could use our knowledge of polynomials to piece this together. Notice that this is an x cubed function, so the end behavior of this polynomial would be like an x cubed. So that's going to look like a, what? Like a whew. So I know over here it has to have be positive, and over here it has to be negative because that's the end behavior of the function. So I know the graph has to be positive over here and it has to be negative over here. If you don't like that argument, you could just test a couple points here. Pick something less than 0. It could be negative 1, could be negative 10, could be negative 100, could be anything. So if I plug in negative 100, well, negative 100 is a negative. Negative 100 minus 2 is still negative. Negative 100 minus 3 is still negative. I get 3 negatives. 3 negatives makes a negative. It should be negative here. Similarly, if you want to test a number bigger than 3, you could try like 100. Same thing. 100 is positive. 100 take away 2 is positive. 100 take away 3 is positive. So I still have positive, so it's positive over here. Now, if you want, you could take advantage of the multiplicities. Note the multiplicity of 0 is 1, the multiplicity of 2 is 1, and the multiplicity of 3 is also 1. Oh, hi, Princess. Oh, my daughter just walked in. Hi, Pumpkin. Daddy's almost finished. Daddy's almost finished with this video. Okay. So if you'd like this at x equals 0, it has a multiplicity of 1, so we know it has to cross through the x-axis. So I know it has to be positive here. Okay, it's got to cross through at 2 since the multiplicity here is 1, so it has to be negative. The multiplicity of the root 3 is 1, so it's got to cross through. Okay, if you don't like this argument, you could also test points. A number between 0 and 1. How about x equals 1? Okay, 1 is positive. 1 minus 2 is negative. 1 minus 3 is also negative. So 2 negatives make it a positive. Positive and positive is a positive. Same thing over here. If you do 2.5, a number between 2 and 3, 2.5 is positive. 2.5 minus 2 is positive. And 2.5 minus 3 is negative. So 2 positives and a negative, well, that makes a negative. So we can see here, when is this function bigger than 0? That's when x is between 0 and 2, or when x is bigger than 3. So we can go ahead and write that down. Okay, so we need to record those intervals. So it looks like x could be between 0 and 2, or x could be bigger than or equal to 3. Okay, this would be in set builder notation. We could also say that x is between 0 and 2, or x could be bigger than or equal to 3. You could equivalently write that, right here you could say that x is between 3 and infinity. It's also equivalent. Or we could say, where are we going from? We could go from 0 to 2, hard brackets on both of those, and I use this union sign, or I could be bigger than 3, so we'll put a hard bracket on 3, we'll go to infinity and a soft bracket. So set builder notation, inequality notation, or interval notation. All three of these would be the same. So I hope you found this review of finding the domain of functions useful. We'll be using this a lot in the coming sections. We'll see you then. Take care.